This is the second part of the module on fundamentals of radiation, radiative properties. Radiation leaving a surface, or we call it emission, can propagate in all possible directions, 360 degrees. A hemisphere above the surface, 180. Now, incident radiation may come from all possible directions. Again, 360 degrees, hemisphere about 180 above. Emitted and incident radiation are generally not uniform. Yeah? So, it's not the same which that comes from one direction compared to the other. We're interested to know the magnitude of the directional distribution, what we call radiation intensity. The manner a surface responds to incident radiation, irradiation. Incident radiation is called irradiation. The manner a surface responds to it depends on the direction, which direction it comes from. The magnitude of radiation emitted in this case, and incident, in a specified direction in space is called the radiation intensity. Now, radiation intensity is used to describe the emitted radiation that varies with the zenith, theta, and azimuthal phi angle. If radiation emission is uniform in all directions, like a black body, the emissive power would be sufficient to quantify the radiation. But then we don't have a black body in real life. So you have to know the specified direction and the directional distribution. We look at the schematic figure here. So we have an emission from a differential area dA1 into a solid angle d omega subtended by dAn at the point dA1 here. Now, this is the spherical coordinate system. So you have to understand this is the zenith angle, this is the azimuthal angle. The differential solid angle d omega, the units is steradian. Pi in engineering is radian. Solid angle is in steradian. Subtended by a differential area ds on a sphere of radius r can be expressed as 1211. So this is ds on the sphere. The differential area dan is considered as a differential rectangular element of dimension r d theta, r sin theta, d phi, this area. So you have differential area an as given by this. From 1211, then you have d omega ds over r squared given by 1212. It's a projected area where alpha is the angle between the normal to the surface and the direction of viewing. For small surfaces viewed from relatively large distances, 1212 may be approximated by just this. This is very large, so you just approximate it by the area viewing divided by the r squared, the distance. For example, here is given in your book, the solid angle subtended by a 5 cm squared plane surface when viewed from a point O at the distance 80 cm along the normal of the surface is just this, in steradian omega. The intensity, I subscript lambda because it depends on the wavelength, emission, it's a subscript E, is the rate at which radiant energy is emitted at the wavelength lambda in the direction theta and phi per unit area of the emitting surface normal to this direction per unit solid angle about this direction and per unit wavelength interval d lambda about lambda. Yes, that is a mouthful, but that's the definition of intensity. It has the unit watt per meter squared per steradian per micrometer. The radiant energy or flux from the differential area dA1 is the emissive power per unit area of the emitting surface given by 1214. If the emitting surface is a diffuse emitter, now the intensity is independent of direction, independent of theta and phi. Then the emissive power is just pi multiplied by the intensity, watt per meter squared, given in 1216. Pi again in steradian based on actual surface area of the emitting surface. What does it mean to be a diffuse surface? So a surface which is diffuse has its properties independent of direction. Now, if the surface is said to be grey, its properties are independent of wavelength. So we have for black body, which is a diffuse surface, the emissive power is just pi multiplied by the intensity given by 1217. The intensity of a black body radiation at the absolute temperature T is given by 1218. See, the black body radiation is just pi T to the power 4. Remember, temperature is always in Kelvin. Incident radiation from all directions onto a surface, that's the term irradiation, symbol G, falling on the surface. For diffuse incident irradiation, independent of theta and phi, we have the irradiation, G, and we got 1220. Next, radiosity, symbol J, is the total thermal radiation leaving a unit surface area in a unit time. That is emission plus reflected irradiation. For black body, of course, the reflected irradiation is 0 because everything irradiated is absorbed. If the surface is a diffuse reflector and a diffuse emitter, since radiosity is a total radiation due to emission and reflected irradiation, you have 1222. Subscript I means on the I is for emission and irradiation and radiosity. To quantify the emission, absorption, reflection, and transmission concepts, the spectral and directional effects have to be addressed. But we will simplify much of this in our radiation analysis. The total emissive power E, watt per meter squared, is the rate in joule per second at which radiation is being emitted per unit area at all possible wavelengths and in all possible directions. E does not include reflected radiation. E depends on the material, surface conditions, smooth or rough, and surface temperature. The ratio of the intensity of the radiation emitted by a real surface to the black body at the same temperature is the emissivity. It's tabulated in your appendix. The equation is 1233 with respect to black body. Emissive power. Now, since the black body is a diffuse emitter, its intensity is given by just EB divided by pi. So here, I like these schematic diagrams, not in your eBook. We have here the relationship between reflected irradiation, the transmitted irradiation, and the absorbed irradiation, the fractions of each of these total unity. So alpha, or the absorptivity, is a fraction of irradiation that is absorbed by the surface. Rho is the reflectivity, is the fraction of irradiation that is reflected by the surface. Is a portion with respect to the irradiation. And tau is the fraction of irradiation that is transmitted, transmissivity. Most transparent and translucent solids do not transmit. So that means your tau is 0, so you only end up with alpha plus rho is equal to 1, 1241. Most gases do not reflect, so you have only the absorption and the transmitted portion, 1242. Actually, in general, it's difficult to determine alpha, rho, and tau because they depend on the upper and lower surfaces, the wavelength, as well as the composition and thickness of the medium. We shall see later how this may be simplified to make our analysis much simpler. Emission from real surfaces. A real surface emits less energy than a black body. Black body is ideal. The emissivity of metallic surfaces is generally small, as low as 0.02 for highly polished gold and silver. As you can see in your appendix, highly polished gold is about 0.03 up to 0.06, and polished silver is 0.02 up to 0.07. Quite low. The emissivity depends strongly on the nature of the surface, influenced by fabrication, thermal cycling, and any chemical reaction with the environment. And with the presence of oxide layers, the emissivity may significantly increase. The metallic surfaces, as you can see here, polished and heavily oxidized, they differ. The emissivity of conductors is generally large, exceeding 0.6. The emissivity of conductors increases with temperature. The emissivity of non-conductors may increase or decrease with increasing temperature. As you can see here, for concrete, it increases with temperature. Yeah, with ice, it increases with temperature. Non-metals, and this one is increasing, this is decreasing. Now, Kirchhoff's law is to simplify our radiation analysis. Kirchhoff's law states that the total hemispherical emissivity of a surface at temperature T is equal to its total hemispherical absorptivity for radiation coming from a black body at the same temperature, given by 1247. It's much simplified earlier. Yeah. So this is under the condition that the surface temperature is equal to the temperature of the source of irradiation, or has a small difference, of course, but not a few hundred degrees. The relation is valid for irradiation or the emitted radiation, which is independent of direction. That means it's diffuse. So you may apply this if you assume the surface is diffuse. Okay, that wraps up the module on fundamentals of radiation.